Hello everybody, it's Mr. Pope from Wilmington Grammar School for Boys. Yep, I'm going to be doing another senior maths challenge from 2017. Haven't seen this one in a long while. I may have gone through the answers at the time when I was teaching in 2017. Well, I'm still teaching now, but I mean like when I was teaching people at the time in 2017. To be honest, I can't remember any of the questions from it. Yeah, I thought I'd just go through some stuff today. Um, I think quick little combinations thing. Um, Suppose I wanted to work out the combinations or the amount of permutations, sorry, of, let's say, the word leads. Okay, now leads has got a repeated letter of E. So the way to work out how many combinations leads can be done in is you count up how many letters, 1, 2, 3, 4, 5. So it's 5 factorial, and this is all going to be over. And then you just count how many individual letters there are. So there's one L, so that'll be over 1 factorial. There's two E's, so that'll be 2 factorial. There's one D, so that'll be 1 factorial. And there's one S, so that'll be 1 factorial as well. The 1 factorials are all just 1, so that cancels down. So 5 factorial is 5 times 4 times 3 times 2 times 1. And 2 factorial is just 2 times 1. They cancel. 5 times 4 is 20, times 3 is 60. Now that might save you a little bit of time instead of writing down all 60 combinations, making sure you haven't, you've got them all, and so on and so on. Anyway, let's crack on. So let's get my timer. So it's 90 minutes. I'll try and be quicker than that. It's multiple choice, letters A to E. You start off with 25 marks, and you get 4 marks for each correct answer. You get nothing if you leave it blank, and 1 mark is deducted for each incorrect answer. I'm not sure of the grade boundaries, but ideally a score between 95 and 100 would be very good. You'd be definitely Olympiad, well, follow-on questions from that. I mean, a score of about 75 is pretty respectable. Anyway, let's just give it a go, see how it goes. So right, so 3, 2, 1, go. Right, okay. One of the following numbers is prime. Which is it? Okay, 2017 minus 2 is 2015, that's a multiple of 5. 2017 minus 1 is 2016, that's even. 2017 is prime, so it could be that. 2017 plus 1 is even, and 2017 plus 2 is 2019, and 2 plus 0 plus 1 is 3, plus a 9 is 12, so that's a multiple of 3, so it has to be 2017. So even if you're not particularly prepared, at least you know 2017 is prime, which is nice. So if they pull any other 2017 questions, you can go straight in. Okay, last year an earthworm from Wigan named Dave wriggled into the record books as the largest found in the UK. Dave was 40 centimetres long and a mass of 26 grams. What was Dave's mass per unit length? So we want grams per centimetres. So he was 26 grams per 40 centimetres. Okay, so I just need to do 26 over 40, which is the same as 26 over 4, and then divide by 10. So 4's into 26 goes 6, with 2 left over, so that's 5. So I make that 6.5, but then divide by 10 makes 0.65. Okay, yeah, that's fairly straightforward. Question 3. The 5 integers 2, 5, 6, 9, 14 are arranged in a different order. In the new arrangement, the sum of the first 3 integers is equal to the sum of the last 3 integers. Okay, so you've got 1, 2, 3, 4, 5 in order. My gut instinct is that 14 is a lot larger, so if I put that in the middle, is it possible to make pairs from the remaining 4 that add up to the same? And I think 2 and 9 is 11, and 5 and 6 is 11. So if I say maybe 2, 9, 5, 6, then these 3 will equal these 3, because this is clearly 11 plus 14, the last is 11 plus 14. So the middle number has to be an E, which is 14. Which of the following is equal to 2017 minus 1 over 2017? Or over a common denominator, this is 2017 squared minus 1 over 2017, and 1 is just 1 squared. It's a difference of squares. So 2017 plus 1 is 2018 times by 2017 minus 1, which is 2016, all over 2017. So yeah, it looks like it's the last one. Okay, 1 light year is nearly 6 times 10 to the 12 miles. In 2016, the Hubble Space Telescope set a new cosmic record, observing a galaxy 13.4 thousand million. Right, 1,000 is 10 to the 3, and a million is 10 to the 6. So when I times them together, that's 10 to the 9. You add the powers, and this is 13.4. And 13.4 times 10 to the 9 is 1.34 times 10 to the 10. Okay. Right. So 1 light year is nearly that many miles, so I need to times 1.34 times 10 to the 10 by how many miles, which is 6 times 10 to the 12. So 6 times 1.34, well 6 times the 4 is 24, 6 times the 3 is 18, plus the 2 is 20, 6 times the 1 is 6, plus the 2 is 8, so it's 8.04, add the powers, 8.04 times 10 to the 22, which is roughly 8 times 10 to the 22, so the answer appears to be C. Seems legit to me. Okay, 6 circles in the diagram to be coloured so that any 2 circles connected by a line segment have different colours. What is the smallest number of colours required? Okay, let's assume 2. So if I say the middle is 1 colour, then this must be different, this must be different, this must be different, and this must be different. We run into a problem because these 2 are connected and they can't be the same. However, I could make these other 2 along that diagonal the same as well. So I need 3 colours to do this. There's not a lot we can do here. And it's this connection here that's causing the problem, so it's just 3. No trick to that. You can just see it quite quickly. The positive integer k satisfies that. So root 2 is just root 2 plus 8 root 8, which is 2 root 2 plus root 18, which is 3 root 2. So in total, we've got 6 lots of root 2, which is root 36 times root 2, which is root 72. So yeah, k is just 72. That wasn't particularly difficult, just be good with surds. So already, with 5 minutes in, I've got 7 fours, 28, plus the 25. I'm now on 53. I've probably got a bronze medal already, so I don't... if you just take your time and bang out the first 10 questions, I don't see why you can't get at least a certificate for these things. Anyway, when evaluated, which of these is not an integer? Well, 1 to the minus 1 is an integer, so that's out. 4 to the minus half, well, that minus power becomes 1 over, and then to the half means square root of 4. Well, 1 over the square root of 4 is a half, so that's not an integer. 6 to the 0 is an integer, that's 1. 8 to the 2/3 means you cube root 8 first to get 2, then square it to get 4, so that's not an integer. That is an integer. And 16 3/4 is you take the 4th root of 16, which is 2, and then cube it to get 8, so that's an integer as well. So yeah, 4 to the minus half is the only one that's not an integer. Right, the diagram shows n by n plus 1 rectangular tiles with k times k plus 1 rectangles. Wait. It shows an n by n plus 1 oh, okay, so that n by n, okay. So if that's n, then the whole thing is n, okay, fine. And then inside of it is k times k plus 1, where n and k are integers, and k takes each value from 1 to 8. Right, okay, what is the value of n? Okay, so the smallest rectangle is going to be 1 along by k plus 1, which is 1 plus 1, 2 wide. Now that means this rectangle must be 2 wide by 3 along. What can we deduce here? So this is 2. Whether this is drawn to scale or not. Okay, we've got 2. I don't want to guess, but I'm pretty sure. Where must the 3 by... This must be the 3 by 4 one, and this must be the 4 by 5 one. And if this length here is 5, this must be the 5 by 6 one, because this length is 5 plus 2, that's 7. Oh no, that's not right. Yeah, hold on. That's 6 plus the 2 is 8, and I've got a 5 by 3 there. Yeah, that works. Okay. Which means this must be the 6 by 7. So in actual fact, we've got this down, haven't we? Because we've got 7, 5, and 4. 7, 5, 4. We've got 7, 5, and 4. So that's 9. So that's 16. What is the value of n? Well, for the n plus 1, but we don't know if that's the n or the n plus 1. Okay, so where were we? 6 by 7. Okay, so the only two ones I've got left is the 7 by 8 and the 8 by 9. Well, if this is 3 and that's 1, that's 4, this must be 8 wide. So this must be 8 along, so this must be the 8 by 9. And this is the 7 by 8. Okay, yeah, that's fine. Yeah, so you've got a 9 along here and a 6 along here, so that's 15. It's 15 by 16, so the n is 15b. Okay, yeah, it wasn't too bad. Right, a rectangle is divided into 3 smaller congruent rectangles as shown. Each smaller rectangle is similar to the large rectangle. In each of these 4 rectangles, what is the ratio of the length of the longer side to that of the shorter side? Okay, so I don't know, let's call the short side the little one x and that long side y. So what is the ratio of the length of the longer side to the shorter side? So the longer side would be y to x, and that ratio must be the same. So this is for the small rectangles, this must be the same for the large ones, and the large one would be the length, which would be 3x, to the width, which would be y. Okay, and when we've got this, we've got the relationship y over 3x equals to x over y. So I can times across both sides to get 3x squared equals y squared. I can square root both sides to give y equals to root 3x. I take the positive root because we're dealing with real lengths here. So that means I have to multiply, when x is 1, y is root 3. So it's in the ratio of root 3 to 1. So the answer is D for there. That wasn't too bad. Yeah, I'll take that. Seems legit. Okay, question 11. The teenagers Sam and Joe notice the following facts about their ages. The difference between the squares of their ages is 4 times the sum of their ages, and the sum of their ages is 8 times the difference between their ages. Right, this is clearly a quadratic. I'm going to need some space. Give me some space. Right, okay, so what am I saying? So the difference between the squares of their ages. So I'm going to call Sam A and Joe B. So the difference between the square, so it'd be a squared minus b squared, that will equal 4 times the sum of their ages, which is a plus b, and the sum of their ages, which is a plus b, equals 8 times the difference in their ages, a minus b. And it doesn't matter, I'm just going to let the a one, you know what, I don't even have to define either of them. All I'm going to say is that a is bigger than b, so a is the older one. Okay, this is a pair of simultaneous equations, one linear and one's not linear. So what I'm going to do is I'm going to take the linear one and make either a or b the subject. So if I expand this, I'm going to get a plus b equals to 8a minus 8b. So if I add 8b to both sides, so this is a 9b, and then a minus a from both sides, at 7a. So I don't know, let 9b, well, let's make b the subject. So let's have 7a over 9 equals to b. And then I'll substitute up into there. So we're going to have a squared minus b squared, which is 49a squared over 81 equals 4 lots of A plus B, well 7 ninths plus 9 ninths is going to be 16 ninths. So 4 times 16 is going to be 64. So this is 64A over 9. Oh boy. Okay. So let's tidy this stuff up first. 81 minus 49. Just real quick. It's 32. So this is going to be 32A squared over 81 minus the 64A over 9 equals to 0. I noticed that 32 and 64 have a common factor, so does 81 over 9. So if I take 32 over 9 lots of A out as a factor, then I'll have A over 9 as the first term, and I'll just have minus 2 over here. Is that right? I haven't paused this up. So either 32 over 9A equals to 0, which means A equals 0, which is dumb, or A over 9 minus 2 equals to 0, which means A over 9 equals 2, so A equals 18. And then that means B is divide that by 9 to get 2, and then times by 7, so that B is 14. Where are we? Question 11. So the oldest one's 18, the youngest one's 14. It says, what is the age of the older two? It's the 18. Okay, question 12. The diagram shows a square and a regular decagon that share an edge. One side of the square is extended to meet an extended side of the decagon. What is the value of x? Right. Okay, I've got a 1, 2, 3, 4. Is that a four-sided shape? Yeah, it looks to be. Okay. Right, let's work out some angles then. So, decagon. I know that this angle here must be 36 degrees because 360 divided by the number of sides for a regular polygon is going to be the exterior angle. This is clearly an exterior angle, so that's okay. What else have we got? We've got that this is 90. If this is 36, the interior angle is 180 minus 36, which I believe is... Let me get a smaller pen. So this is 36, this is 144, this is 90, this is 144, this is 90 as well. So actually this angle we can work out as well quite nicely, because 144 plus 90 is 234, 360 minus 234 is... So that's 126 degrees. Okay. Okay. There's lots of ways you could do this. You know what? I'm going to try something. I'm going to try the argument of rotation. So what do I mean by that? I mean, no, I'm not. No, what could I do? Hold on, I've just said this is a 1, 2, 3, 4-sided shape. So, yeah, I just add them all together, right? So I've got x, which is that angle, plus the 90 up there, plus this angle here, which is 90 plus 126, which is 216, plus the 36 down there. This must equal 360. So all I have to do is add these together. 216 plus 90 is 306, plus 36 is 342. So what, x is 18 degrees? Is that what we're saying? Seems legit. Yes, 18 is an answer. I'll go for that. Okay. Yeah, that's probably what I'd have gone for. Okay, right. Oh, logic things. Okay, so question 13. Isabel says Josh is innocent. Josh says Jenatan is guilty. Jenatan says Tegan is guilty. Tegan says Isabel is innocent. Only the guilty person is lying, all the others telling the truth. Who is guilty? Right. Boolean logic here. I'm just going to assume, to start off with, that Isabel is telling the truth and see what happens there. And once I've gone through that, I'll then say, well, let's assume she's the guilty person. So if Isabel is telling the truth, then that means Josh is innocent. If Josh is innocent, then Josh is telling the truth and Genatan is guilty. If Genatan is guilty, then he's lying by saying that Tegan is guilty, which means Tegan is innocent. And if Tegan is innocent, she's telling the truth about Isabel being innocent, which she is. So in this example, if Isabel is innocent, then it's clearly Genatan that's the one that's guilty here. Let's assume that Isabel is guilty. If she's guilty, then she's lying about Josh being innocent, which means Josh is guilty. And if Josh is guilty, then he's lying about saying that Jenatan is guilty, so that means Jenatan is telling the truth. If Jenatan is telling the truth, then that means Tegan's guilty. And if Tegan's guilty, she's lying about Isabel being innocent, which means Isabel is lying. Well, look, in this case, we've got 1, 2, 3 people lying and only Jenatan telling the truth. Well, I'm guessing from the wording that only the guilty person, singular, is lying. So in the example when Isabel is lying, that means 3 people are guilty and there's only supposed to be 1 guilty person. So to me, it looks like Jenatan is the guilty party here. I guess. Makes sense to me. Okay. In the diagram, all the angles marked dot are equal in size to the angle marked x. What is the value of x? Okay, right, I'm definitely going to be doing a rotation thing here. Okay, right, easy peasy. Imagine I'm an ant and I'm starting from here and I'm walking this way. Right, and as I walk along, I get deflected by this angle and I keep walking along and I get deflected by this angle and I keep walking along, I get deflected by this angle, keep going along, deflected by this angle, keep going along, deflected by this angle, and then deflected by that angle, deflected by that angle, deflected by that angle, and then deflected by this one, and I'm back where I started. What's important is the net rotation. So what do I mean by that? Say this is the direction I'm going. As I'm going along and I'm walking, then I turn like that, and I keep going, and then I turn like that. And all we need to do is just keep a track of how many times we've rotated. Keep going. And now at some point when I reach here and I start turning like that, I'm going down. But now, when I turn from going that direction to this direction, I have somehow gone from there. I've gone from pointing that way to parallel of how I initially was. So I've turned 360 degrees anti-clockwise, and now I'm heading up this way. So it's one turn. It's more than a turn. I keep going around there, and I keep going around here. I keep going, keep going, keep going. And when I get back to there, it's 2 turns. So the net rotation has been 2 turns. And I know what 2 turns are. 2 turns are 720 degrees. Then finally, I have done 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? So initially I'd have gone 1 turn, 2 turns, 3, 4, 5, 6, 7, 8, 9. Yes, 9 turns. So I've done 9 lots of 180 degrees minus my angle x. So if I divide by 9 both sides, 720 divided by 9 is 80. So 180 minus x is 80. X is clearly 100 degrees. That's fairly straightforward. Yep, x is 100 is one of the answers. Lovely jubbly. Okay, the diagram shows a square PQRS, okay, square. Points TUV and W lie on the edges of the square as shown, such that P to T is 1. Okay, so that's 1. Q to U is 2. R to V is 3. And S to W is 4. The area of TUV, which is this weird frustum type shape, is half of the whole square. What is the length of P to Q? Right. Okay. Right. So, if I call, let's say T to Q. T to Q is the largest. Then this square is a 1 plus x all squared thing. So, what must this be so that when I add 2 to it, the whole thing is 1 plus x? This is clearly x minus 1, isn't it? And then this must be x minus 2, and then this must be x minus 3. Okay, fine. Then we also know that x plus 1 all squared is double all of this frustum bit here, which also means actually that it's double all of the triangles, right? Because if you take half of it away, i.e. the frustum, you're left with the other half, which is the triangles. And the triangles are easy to sort out. It's just going to be a half of base times by height for each one. But since we're timesing it by 2, then all I have to do is just multiply all the bits together. Oh, that's nice. This looks like it's going to be a quadratic. So from the bottom left triangle, this is just going to be 1 lots of x minus 3, plus the bottom right triangle, which is 2x, plus the top right triangle, which is going to be 3 lots of x minus 1, and the top left triangle is just going to be 4 lots of x minus 2. Right, so what we're going to have here, I'm going to have x plus 1 all squared equals, I've got an x there, 2x there, a 3x coming out, stop it, what's going on here, a 3x there and a 4x there, so 1 plus 2 plus 2 plus 4 is 10, so I'm going to have a 10x popping out, and I've got a minus 3, a 3 minus 1, 3 times minus 1, which is another minus 3, so it's minus 6, and 4 times minus 2 is minus 8, so minus 6 minus 8 is going to be minus 14. This looks like a nice quadratic to solve, so I'm going to have x squared plus 2x plus 1 equals 10x minus 14. So if I add 14 to both sides, it's 15. For minus 10x, it's going to be minus 8x and x squared. Oh, that's nice, because that's going to factorise to x minus 3 times x minus 5. So either x equals 3 or x equals 5. Why is that good? Because if x equals 3, then this thing is 0. So it has to be that x equals 5. It's the only one that makes sense. So if x is 5, then that's 1 plus 5. So the whole length from P to Q is 6. Yeah, boy. So P to Q, that's just B, 6. All right, so what are we on? 85? Yeah, you're definitely in the golds now. Yeah, this is, wow, 26 minutes. Yeah, hopefully I'll finish this pretty quickly. Right. So the diagram shows 2 right-angled triangles inside a square. The perpendicular edges of the larger triangle have lengths of 15, 20. Right. Okay. Well, first of all, whatever angle this is, let's call it x. Then this angle here is 90 degrees minus x, which means this angle is x, which means this one is 90 minus x. That's good, because then that means that the 2 triangles, this one and this one, are similar. So one's a scaled up version of the other. Because, is this a square? The diagram shows 2 right-angled triangles inside a square. Yes, inside a square. Okay, so then that means if I know that's 20, then this length here is also 20. This 15, 20 is clearly a 3, 4, 5 triangle. So now I can work out what this thing is, because if I've got a similar triangle where now this is 20, what do I have to do to get from 25 to 20? I divide by 5 times by 4. So 20 divided by 5 times by 4 is going to be 16, and 15 divided by 5 times by 4 is 12. So that means this length here is 12, and this is not 14, this is 16. So what's the question we want me to do? What is the area of the shaded quadrilateral? Well, I do 15 times 20 and halved it, which is 15 times 10, which is 150 for that bottom triangle. And 12 times 16 and then halved it is the same as 6 times 16, which I believe is 96. 6 tens are 60, 6 6 are 36, yes, okay. 96 plus 150, I believe is 246. And I have to take that away from a square that's 20 by 20, which is 400. So I have to add a 4 to this. That's 254, isn't it? Oh, geez, no. 154. Yeah. Yeah, seems legit to me. And yes, 154 is one of the answers, so I'm going to go with that. Oh, God. Amy, Beth, and Claire each have some sweets. Amy gives 1/3 of her sweets to Beth. Beth gives 1/3 of all the sweets she now has to Claire. Then Claire gives 1/3 of all her sweets she now has to Amy. All the girls end up having the same number of sweets. If Claire began with 40, how many sweets does Beth have? Okay. Okay, right. Systems of equations. Gee damn. Okay, so let's say so all we know with Amy is that well, it must be divisible by 3, right? Because she's 2 and some thirds. So what does Amy now have? She now has 2/3 of her original sweets. Beth now has her original sweets plus 1/3 of Amy's. And then when Beth gives 1/3 of her sweets, that means Claire is going to have her original sweets plus 1/3 of what Beth gave to her, which is going to be what she had originally plus 1/3 of A. And then Claire gives 1/3 of her sweets now to Amy. So then Amy will now have 2/3 of what she had originally plus 1/3 of what Claire has, which is C plus 1/3 of B plus 1/3 of A. Now, Beth has 2/3 of this amount because she gave 1/3 away, and Claire now has 2/3 of this amount. So now we just have to set all these three things equal to each other. Oh dear, is there a quicker way? Probably. Oh, I've set up the equations now. Okay, well, let's just deal with it. They're all going to be fat powers of 3, so whatever. So I've got 2/3 of A there, and I've got 1/3 of 1/3 of 1/3 of A. So it's going to be 1/27. So it's 2/3 plus 1/27. Times this by 9 top and bottom, so it's going to be 19/27 A. How many B's? I've got 1/3 of 1/3 of B, so that's plus 1/3 of B. Let's tidy this up. 1/9 of B is going to be 3/27, and then the amount of C's is 1/3 of C, so that's going to be plus 9/27 of C. Right, that's how much that person's got. Right, for the next one, I've got 2/3 of 1/3, which is 2/9, times by 3 is going to be 6/27, yes, A, plus 2/3 of B, if I times that by 9 top and bottom, that's 18/27 B, and no C. And then for the last one, I've got 2/3 of 1/3 of 1/3, so that's 2/27 of A. And then I've got 2/3 times 1/3, which is going to be 2/9, so that's 6/9 of B. And then I've got 2/3 of C, if I times by 9, that's going to be 18/27 of C. Right, they all equal to each other, so I could just scale this question up. Oh no, did I do 6/9? I shouldn't have done that. How many B's? 2/3 times 1/3 is 2/9, so that's 6/27, yeah. Okay. Right, the reason I've done that, 1, is because I'm silly. No, for 2, it's because if they're all the same, if this equals this equals this, then I can times everything by 27 and the proportions are kept the same. So that's nice because then the 27s can all disappear and I'm not dealing with fractions anymore. And now I can start to solve simultaneously. Okay, so let's figure these two out. So if I do one minus the other, 19a minus 6a is 13a, and 3b minus 18b is minus 15b, and then 9c minus nothing is just 9c, and this equals to 0. So I'm actually going to get 13a plus 9c equals to 15b. Is that right? Okay, sure. That's one equation. I could do the same here. So 2a minus 6a is 3. Whoa, geez, no. 2a minus 6a is minus 4a. 6b minus 18b is minus 12b. And 18c minus nothing is just going to be 18c, and this equals to 0. So if I whack that over to the other side, I'm going to get 4a plus 12b equals to 18c. If I jiggle that around, I can divide all of this by 2, can't I? So 4a becomes 2a, this becomes 6b, and this becomes 9c. Right, no, this is good, because now I can substitute this into here. So I've actually got 13a plus 2a, which is 15a, plus a 6b equals to 15b. And if I minus 6 from both sides, this is a 9b. So that means 15a equals to 9b. Is that right? If I made a boo-boo there. 13 plus 2a. 15 minus 6, definitely 9. Okay, so I can divide by 3 both sides to get 5a equals to 3b, which means that a to b is in the ratio of 3 to 5. So whatever Beth had, for every 5 that Beth had, A has got 3. Now, okay, well that's interesting because I can take this 5A to 3B back into here. And I know for every 3B is 5A, so it's actually 2A plus 10, so that's actually 12A equals to 9C. I can divide this by 3 to get 4A equals to 3C. So that means A to C is in the ratio of 3 to 4, and luckily we've got A's in the ratio of 3 to 3. So now I've got A, B to C is 3 to 5 to 4. Groovy, we're cooking with gas. So if Claire began with 40 sweets, that means we need to scale these all up by 10, so it's 30, 50, 40. So how many sweets does Beth have originally? She has 50. Yeah, it wasn't too bad, just a bit messy. Tidied up as we've gone along. Probably spent a bit too much time, but I've got a good hour to go. It's fine. Wait. Have I done this question already? Wait a minute. Yeah, it's question 11. Oh dear. If I copied the wrong thing. Whoops. Okay, fine. So we'll get rid of... That's weird. Yes, last questiones. Right, 18. The arithmetic mean A of any two positive numbers x and y is defined to be... Yeah, that's the arithmetic mean. And the geometric mean G is defined to be that for two particular values x and y, with x being bigger than y, the ratio of A to G is 5 to 4. Okay, so for every 5 of the arithmetic mean, the geometric is 4. So that means if I've got 5 lots of the geometric mean, which is 5 root x, this is going to be 4 lots of a half, which is 2 lots of x plus y. So now I just need to find x in terms of y for this relationship. Fine, so this isn't bad. We just square both sides. So we're going to get 4 lots of x plus y all squared equals to 25 lots of xy. Square this thing really quickly is going to be 4x squared plus 8xy plus 4y squared. This equals to 25xy. Subtract it over. We're going to get 4x squared minus 8 minus 25 minus 17xy, and then plus 4y squared equals to 0. Oh man, does this factorize? Maybe. You know what? I'm not going to waste time factorizing. I'm just going to complete the square. So I've divided everything by 4. I've got x squared minus 17 over 4xy plus y squared equals to 0. Half of 17 over 4 is 17 over 8. So if I do x minus 17 over 8y squared, That will generate the x squared and this term, but I'll have to minus a 17 squared over 8 squared. I won't deal with that just now, y squared, and then plus a y squared. This equals to 0. The reason I won't do that is for reasons. And y squared is 8 squared over, yes, okay, common denominator time. So when I come to solve this, I will have x minus 17 over 8y all squared equals to y squared lots of 17 squared minus 8 squared over 8 squared. Oh, is that a thing? 17 squared is 289. 8 squared 64. 9 minus 4 is 5. 2. Ooh, 225 is 15 squared. Yeah, boy. Okay, cool. It's useful to know your square numbers really quickly. If not, you probably could just work that out. So if I square root both sides, I'll have x minus 17 over 8y equals plus or minus 15y over 8. Oh, that's nice, because then that becomes x equals y lots of, and then it will be 17 plus or minus 15 over 8. So x is going to either equal to 17 plus 15, 32, oh, 4y, nice, or x is going to equal to 17 minus 15, which is 2, 2/8, or a quarter, so this is y over 4. Okay, we've got that x is bigger than y. Okay. Well, in that case, if x equals 4y, then this is the only one where x is bigger, right? Because if I've divided y by 4 to get x, that means that y is bigger than x. So it can't be that one, so x has to equal 4y. So if I want the ratio of x to y, that means for every 4x, there's 1y. So it's 4 to 1, so I'm going with E, 4 to 1. Yeah. Yeah, no, okay. Right, the diagram shows a circle of radius 1 touching 3 sides of a doodah. Diagonal of the rectangle intersects circle point at P and Q. What is the length of the chord P to Q? Right, I don't know how useful this is, but if this is a radius 1, so the centre's like that, so Bosch. Okay, so that means, does that mean it's flat, horizontal? Is that true? Is that 90 degrees? Well, if it's a 2x4 rectangle and there's a radius of 1, then that means you've directly cut this in half. So by symmetry, there must be another circle. There potentially is another circle here with radius 1, where that's the same as Q. So that distance there, okay, fine. What else do we know? If this is a 2x4, then from here to here is 2, and from here to here is 1. So that means from here to here by Pythagoras is root 5. So my gut instinct it's root 5 minus something. So it looks like this one. Okay. Right, if I draw a line from here to here, so that's 90. This angle, which is part of that, is the same as this. Oh dear. Oh man. Is this twice we've had similar triangles? Okay, I spot a theme here. Okay, so if I consider this triangle, which has base like this, that's 2, that's 1, that's root 5. And now I consider this similar triangle, because it's got a 90, it's got 2 angles that are the same. Well, it's got all 3 angles the same. So then if I flop that around, then what have I got? I've got that I want to find this thing we'll call x. I don't know what this thing is, but I know the hypotenuse is 1. So to go from root 5 to 1, I just divide by root 5. So x is just going to be 2 divided by root 5. That's clearly half. So I just double it. So it's 2 lots of root 5. Yeah. Okay, 4 over root 5. Yeah, that makes more sense. How are we doing for time? Yeah, half time. Okay, no, okay, fine. Let's make this smaller. Whack it over here. Okay, 20. The diagram shows a square PQRS with edges of length 1 and 4 arcs, each of which are a quarter circle. Wait, what? And 4 arcs, each of which are a quarter circle. Arc TRU. Oh, jeez. Wow, okay. Arc TRU has centre P. VPW has centre R. UV has centre S. Oh, wow. Okay. That's a weird shape. What is the length of the perimeter of the shaded region? Okay. Interesting. Okay, well, first of all, if I look at just this sector here, the UPT one, then this arc clearly has a radius of the diagonal of this square. And if it's of length 1 and 1, then this is just root 2 by Pythagoras. And so arc length is just r times theta when dealing with radians. So that's just going to be root 2 times by 90 degrees in terms of radians, which is pi over 2. So this is going to be root 2 pi over 2. And that takes this into account, but also we can sort this thing out. So we've got 2 lots of that. So that total so far is just root 2 pi. Okay. And we can also work out this radius because it's root 2 minus 1. Okay. That's root 2 minus 1 times by pi over 2. And let's double it. So, okay. Interesting. So we've actually got root 2 minus 1 lots of pi plus another root 2 pi. So it looks like we've got pi lots of 2 root 2 minus 1. Is that an answer? Yeah, it's B. Well, that was a nice question. Cool. 21. How many pairs x, y positive integers satisfy the equation 4 to the x equals y squared plus 15? Right, I am definitely having space to do stuff. Okay, so on integers, 4 to the x. Okay, 4 to the x equals y squared plus 15. Okay. Diophantine equation. We're only interested in x and y belonging to the set of integers. Do they have to be positive? Is that a thing? Yes, they were. So this has to be positive integers. Okay. 4 to the x is 2 squared to the x, which is 2 to the x all squared. If I minus the y squared, that's 15. So really, I have to think of a difference of 2 squares that is 15. Difference of 2 squares, that's nice. That's either going to be 2 to the x plus y, and 2 to the x minus y, that equals 15. And because 2 to the x and y are integers, then this must be an integer, because you've got an integer plus an integer. This is an integer as well. So 15 can be broken down into 1 times 15 or 3 times 5. Okay. 2 to the x plus y. Well, because x is positive, this isn't going to be a weird fraction or anything. So this has to be the bigger one. So we're either going to have 2 to the x plus y equals to 5, or 2 to the x plus y equals to 15. And then for the other one, this is going to be 2 to the x minus y equals to 3, or 2 to the x minus y equals to 1. Okay. Right, well, if you add these two together, the y's cancel. So I'm going to have two lots of 2 to the x equals to 3 plus 5, which is 8. Divide by 2, I'm going to get 2 to the x equals 4. So x equals 2. If x equals 2, 2 squared is 4, so then y equals 1. So that was nice. And then same deal, if I solve simultaneously and add these two together, I'm going to get two lots of 2 to the x equals 16. Divide by 2, 2 to the x equals 8, so x equals 3. If x equals 3, 2 to the 3 is 8. 8 plus what is 15, so y equals 7. Is there any restrictions? How many pairs? I can only find 2. X equals 2, y equals 1, and x equals 3, y equals 7. I think that's pretty much it by construction. So I'm going to go for 2. Okay, the diagram shows a regular octagon and a square formed by drawing 4 diagonals of the octagon. The edges of the square have length 1. What is the area of the octagon? Okay. Okay. So it's clearly more than 1. Okay, right. Let's do some maths. So octagon, 360 divided by 8 is going to be 45. So that means this angle here is 180 minus 45, which is 135. So I'm guessing that this is 135 minus 90, which is 45, split in 2. So this is 22. Oh, pen is too fat again. It's going to get messy. Oh, wow. Okay. So this is 135. This is 22.5. This is 22.5. And if I draw a line from here up to there, half of 135 is going to be 67.5. This is 90, this is 90. From here to here, that's root 2, that length is 1. From there to there is root 2, that is 1. Okay. Diagram shows a regular octagon and a square formed by... Okay. Does the center of the square... Ooh, I've got a funny feeling the center of the square has to be the center of the octagon as well. That's nice, because then I think that this length here is going to be root 2 minus 1. So by Pythagoras, we've got root 2 minus 1 squared plus 1 squared equals, let's say, the x of this thing squared. Wait a minute, do I even need to know it? I just want to find the area of the octagon, don't I? So it's just going to be the area of the square 1 plus 8 lots of these triangles, which are here. And if I know that's root 2 minus 1 times 1, that's just root 2 minus 1 all over 2. And if I times it by 8, that's 1 plus 4 lots of root 2 minus 1. So I've got 4 root 2 there. And then 4 lots of minus 1 is minus 4 plus the 1. That's 3. So I make that 4 root 2 minus 3. Which is not an answer. The edge of the square was the area of the octagon. Okay. Maybe my faux pas was that the edge of the octagon... Wait a minute. The edges of the square have length 1. Yeah, that's fine. Well, where have I gone wrong? Do I have 8 of these? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Oh, geez. It's not root 2 minus 1. This is root 2 minus a half, isn't it? Wow. Okay. Yeah, because... Yeah, okay. So it's over half. Okay. But then what's going to happen here is you're going to have 4 lots of root 2, which is 4 root 2, and then 4 lots of minus half is minus 2, so that's 4 root 2 minus 1. You sure? Oh, I've done that wrong as well, haven't I? Oh, you're such a silly boy, Pope. Such a silly boy. No, they're not 1. That's a half. That's a half. So this will be root 2 over 2. Oh, you silly boy. So actually, that's root 2 minus... Okay. No, we can salvage this. So the area is going to be 1 plus, and then it's going to be root 2 minus 1 over 2. Half of that. Half of the times base, which is a half. And then I've got 8 lots of that. Well, the 2, 2, 2, and the 8 will cancel. So I'm going to have 1 plus root 2 minus 1. So the 1's cancel. I'm left with root 2. Yeah. Oh, man, I'm such a silly boy. It's root 2. Yeah. Okay. Just getting ahead of myself there. The parabola with equation y equals x squared is reflected in the line with equation y equals x plus 2. Which of the following is the equation of the reflected parabola? Okay, so if you reflect it in the line y equals x plus 2, well, think about it. What is this instruction saying? You're saying y becomes x plus 2, and the x plus 2's become y's. Okay, so if y becomes x plus 2, this becomes x plus 2 on the... So this y becomes x plus 2, and if x plus 2's become y, that means x's become y minus 2. So this will become a y minus 2 all squared. So this will become x plus 2 equals y squared minus 4y plus 4. If I minus 2 from both sides, I'll get x equals y squared minus 4y plus 2. So I make that C is the answer. Yeah, think about it. If you reflect stuff in the line y equals x, you're turning the y's into x's and the x's into y's. So if you reflect it in the line y equals x plus 2, you're just swapping them over. It's a similar thing. There is a set of straight lines in a plane such that each line intersects exactly 10 others. Wait, what? There is a set of straight lines in a plane such that each line intersects exactly 10 others. Which of the following could not be the number of lines in that set? Such that each line exists 10 others. Really? I'm not going to draw that many lines, surely. Okay. Well, the 11 is true. So, how could we do this? Well, okay. So, unless the lines are parallel, they're always going to meet once, right? Because you can either have lines that are parallel, they meet no times. They're not parallel, they meet once. Or they're something like this, they're on each other and they meet infinite amount of times. We're going to ignore that case because that's just dumb. So they're going to intersect 0 or 1 times. So is it possible for 12 lines to cut through 10 things? Well, I think so. Because surely you could have 1, 2, 3, 4, da 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 da. You could have 10 lines all going through each other like that. Or rather, you could, I don't know, 1, 2, 3, 4. Ah, that's not going to work, is it? So all of them. It's an interesting question. Okay, let's think about this. So if I was to draw, let's say I was to draw 2 parallel lines and then other ones that do stuff. Then if this line here, let's say I draw a load of other lines like that. I draw 4 other lines, it can have 4 intersections. If I draw a parallel line, then it's only going to have 3. It's going to be 1 less because it's going to miss out one of them. So how many parallel lines are there? They're going to have 1 less intersection. So if I've got n lines, which I'm trying to find, aren't I? Then they're going to intersect each other n minus 1 times. Ah, okay, there's n non-parallel lines. That's it. Yeah, because those n lines are going to cut each other n times. So if I draw a parallel one, they're going to cut n minus 1 times. And I want to know how many x's of them there are. Yeah, interesting one. You know what, I've got 30 minutes. I'll finish question 25 and I'll come back to this one. You know, it's a valid strategy. Okay, the diagram shows a regular nonagon moving clockwise around n. Each vertex, the line segment, is drawn perpendicular to the preceding edge. This produces a smaller nonagon. Okay, what fraction of the area of n is the area of S? Okay. Each vertex, a line segment, is drawn perpendicular to the preceding edge. Okay. Right. Okay, so if we call this, if we call this angle x, this is 90 minus x. Can we work out what the angle is? It's a nonagon, right? So 360 over 9 is 40, so that must be 140. Ah, so this must be a 50 degrees. Which makes sense, this has to be a 40. Okay. Yep, that's fine. Right, so if we say this length here is 1, then this distance here is going to be the hypotenuse minus this side. Okay. So I've got stuff in terms of 40, so I might as well use the 40 then. So sine of 40 degrees is going to be 1 over that hypotenuse that I want to do. So actually the hypotenuse is 1 over sine 40. And the adjacent bit, so then cosine of 40 is the adjacent, which we'll call A. No, do we want to do that? No, let's do tan. tan of 40 is the opposite, which is 1 over that adjacent. So that adjacent is 1 over tan of 40 degrees. Now, okay, so I need to do the hypotenuse minus the adjacent. So 1 over sine 40 minus 1 over tan of 40 degrees is that. And for the area, I need to do 1 over 1 minus sine 40 minus 1 over tan 40. That'll give me the length scale factor. Or no, I want the other way around, don't I? If I want the fraction, I want that length over the original, so it'd be that over 1, which does nothing. But then I'm going to need to be wanting to square it to get the area scale factor. Okay, I'll tell you what, let's tidy this up first. 1 over sine 40, 1 over tan 40. Tan 40 is sine over cos. This is actually cosine 40 over sine 40. And this is going to be 1 minus cos 40 over sine 40. So, yeah, so that's the length scale factor. If I do 1 times by this, I get, wait. So to go from big, okay, the big length to the small length, for every one of these, there is 1 minus cosine 40 over sine 40 degrees of that length, isn't there? Really? No, have I done this wrong? No, that's right. So when it comes to the area, then the big one's area to the small one's area is I square the 1 to get 1, and now this gets squared, so it's 1 minus cos of 40 squared over sine squared of 40. Right, okay. And sine squared is 1 minus cos squared. 1 minus cos squared of 40. Okay, and this is 1 minus cos of 40 all squared. 1 minus cos of 40 all squared is just 1 minus cos of 40 times by 1 minus cos of 40. And 1 minus cos squared is 1 minus cos 40 times by 1 plus cos of 40. The minus minus cancels, so I make it 1 minus cos 40 over 1 plus cos 40. Oh, thank you. It's this one. Okay. Truthful time. I have done 24 of the 25 questions. At this point, I've done more than enough to do the British Mathematical Olympiad. I do not know how to do question 24. I would have to work through it. I can't see a way. Okay, there is a set of straight lines in a plane such that each plane intersects exactly 10 others. Oh, I've got 23 minutes. Do I really have to draw all of them? When I've got 11, let's grab a drink. Is it possible with 11? Yeah, it must be possible with 11 because you just have, because you have 11 lines and then 10 unique, well, you have all unique gradients. That's fine because then one line will have, yeah, no, that's fine. Uh, is it possible with 12? Well, yeah, won't it? Because you have 11 unique lines and one parallel. Would that work? Would that work? So if I had 11 parallel, well, let's scale it down. Let's say I had one there, one there, one there, one there. Right, so I have 1, 2, 3, 4 lines, and they all meet each other 4 times. That's so here I'm just dealing with the 4 and 4. So if I drew a parallel line like that, cut 1, 2, 3. Well, hold on a minute. I could move this line up to there. So now they all cut. Yeah. Now they all intersect. No, that's fine, isn't it? So of the 4 lines, they all intersect the other 3 lines. And then if I draw... No, I had it right. Right. If I draw a parallel line... Okay, so this is when it's scaled down when n is 4. So I only need 3 intersections, 1 less. So it was 11, it'd be fine. It would just be a more funky thing. If I drew a parallel line to say that one up there, then I'd intersect with all of them down there. So it'd be one more. So yeah, I think 12 is going to be doable as well. If I could do one more by symmetry over there. I want to say 20 is possible. Right. I tap out. With 20 minutes to go, I tap out. There's not a lot I can do here. So let's grab up the answers. Right, so the right answer was D. Good. I'd crossed these two out. I knew they weren't there. When n non-parallel lines are drawn in a plane, each line intersects every other line exactly once. Yeah, no, I was on the right lines. So each line intersects n minus 1 lines. Okay, so they intersect with n minus 1 lines, fine. A line drawn parallel to one of the existing n line also intersects with n minus 1. Okay, in order that every line drawn intersects the same number of other lines, each of the original n lines must be part of a set of k parallel lines for some integer k. Then kn lines will have k lots of n minus 1 points of intersection. And here, k lots of n minus 1 must equal to 10. And we've got to solve k values for which that work. So as n minus 1 is an integer, n minus 1 must be 1, 2, 5, or 10, giving n. Whoa, 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 whoa. Oh, I see. This is another Diophantine thing. So n minus 1 must be a factor of 10. The factors of 10 are 1, 2, 5, and 10. So that means n is going to be 2, 3, 4 or 11. Of the options given, and then so either n, okay, so either n is 2, in which case k is 10, or n is 3, in which case k is 5, or n is 4. Wait a minute. No, this is 6, isn't it? Yeah, so n could be 6, in which case k is 2, or n is 11, in which case k is 1. Um, of the options given, A is 11 non-parallel lines, so n equals 11 and k equals 1. B is 6 sets of 2 parallel lines. So that's 12, isn't it? So 11 lots of 1. Oh yeah, I've got 11 lots of 1 is 11, 6 lots of parallel lines 12, 2 lots of 10, so I've got 20 lines, and 3 lots of 5 is 15. So yeah, the odd one out is going to be the 16. So there's no way. Yeah, I've got k lots of parallel lines. Wow. Yeah, it's a tricky question. I wouldn't have got that. Hoping you can understand that. Maybe you can try a similar logic for a smaller subset, maybe like 8 lines, or what are the possible ones for when you've got 8 intersections with other lines. Yeah, no, tricky questions. Let's double check, did I get all of these right? That would be an error. Right, 1 was C, yes. 2 was B, yes. 3 was E, yes. 4 was E. 5 was C. 6 was B. 7 was C. 8 and 9 were B. 10 was D. 11 was D. 12 was B. 13 C. 14 A. 15 B. 16 D. 17 D. 18 E. 19 B. 20 B. 21 C. 22 D. 23 C. 24 D, yeah, we talked about, and 25, yes, A. Cool. So apart from that 24, perfect. So yeah, that would have been a score of 24 fours, which I believe are 96, plus the original 25. What's that? 121. So 121 out of 125. Usually 100 would get the British Mathematical Olympiad. But no, yeah, I did not know how to solve those line questions. And now I'm pretty sure I do. You've got to think of multiples of parallel lines and their intersections, and then look at the combinations they could be. So they have to be integers. So you can either have 11 sets. You can have one set of 11 lines, i.e., none of them are parallel, or you can have 2 lots of 6 lines, or rather 6 lines, and then they're all in pairs where they're in parallel pairs, or you can have 3 lots of 5 parallel pairs, and 10 lots of 2 lines in parallel pairs. Wow, really? So hold on, so is that right? So if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'll have another lot, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then apparently, yeah, that makes sense. Yeah, because if I take this line, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, and then, or if I took this line here, it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, no. You just count up the pairs of parallel lines. Yeah. So this is saying so this is the amount of like in tuples, and this is the amount of lines. Cool. really interesting question. I think I get it now. And that's the whole point of going through these things is, you try some maths that you feel fairly confident with, and then you see a really wacky question, you're like, whoa, okay, and it makes you think. And yeah, no, just really good. I've got 12 minutes left, but I think I'm going to end it there. But yeah, thanks, guys. Yeah, there weren't any mistakes, but try these papers, man. They're really good fun. Do as best as you can, and then if you're really stuck, do all the other questions first, highlight the ones you couldn't do. So for me, this one 100% was one I couldn't do. I just carried on. If you really are hitting a brick wall and you've no idea where to begin, or but you feel like, oh, there isn't a quick way, I don't really feel like, there must be some method to it, then yeah, pause the clock and just take it as a learning thing. But, be strict on yourself. I'm not going to award myself those marks. For me, that's imperfect. I've scored 121 out of 125. So yeah, not a perfect run for me. Not great, but there you go. I am only human. I do make mistakes. Don't beat yourself up about it. Anyway, guys, thanks very much, and catch you later.